3%. That was the number. 3% chance of impact. And in the world of asteroid tracking, that number is almost unheard of. Most asteroids that get flagged as potentially hazardous have probabilities measured in fractions of a percent. Hundreds, sometimes thousands. Scientists spend careers watching objects with a 1 in a million shot of hitting Earth. So when an asteroid shows up with a 3% impact probability, agencies like NASA don't just take notice, they move it straight to the top of the list. That asteroid was 2024 YR4, and for several weeks in early 2025, it was the most closely watched object in the solar system. This is its story. Asteroid 2024 YR4 was first detected in December of 2024. It was picked up by automated sky survey programs, the kind that run every clear night, scanning the sky for near-Earth objects and logging anything new. When it was first spotted, it looked like a routine discovery, a rock given a designation added to the catalog flagged for follow-up. But as more observations came in, the picture changed quickly. Early calculations of its orbit showed something unusual. The asteroid had a realistic chance of striking Earth in the year 2032. When scientists ran the numbers through impact probability models, the results came back higher than almost anything seen before. At its peak, the probability of an Earth impact reached roughly 3%. To put that in context, the last time an asteroid reached that level of concern was Apophis in the early 2000s. Even then, the numbers came down relatively quickly. With 2024 YR4, they stayed elevated long enough to trigger a serious, coordinated response across multiple space agencies. Scientists use a system called the Torino scale to communicate asteroid risk. It runs from 0 to 10. 0 means no hazard. 10 means a confirmed global catastrophe. The overwhelming majority of tracked objects sit permanently at 0. Asteroid 2024 YR4 climbed to a Torino scale rating of 3 and briefly touched 4. That had not happened for any object in roughly 2 decades. So what exactly is 2024 YR4? Based on the observations available at the time, scientists estimated it was somewhere between 40 and 100 meters across. That range reflects the uncertainty that exists early in any tracking campaign. As more data comes in, size estimates get more precise. At the smaller end, an impact would be roughly comparable to the Tunguska event of 1908, when an object exploded over a remote region of Siberia and flattened over 2,000 square kilometers of forest. At the larger end, the energy release would be considerably greater. Not a global extinction event, but enough to cause serious regional destruction if it came down over a populated area. The object belongs to a class called Apollo-type asteroids. These are near-Earth asteroids whose orbits around the Sun cross Earth's orbit. It's a common orbital class, and it's the reason these objects come close to Earth in the first place. Their paths and ours intersect at certain points in each orbital cycle. Here is how the situation developed in the weeks after discovery. When an asteroid is first detected, the initial orbit estimate is based on a small number of observations taken over a short window of time. The more the asteroid is watched, the more refined the orbital solution becomes. In most cases, as observations accumulate and the orbit sharpens, the impact probability drops. Because the additional data shows the object will pass safely by. This is a well-understood pattern in planetary defense. Scientists even have informal names for it because the probability often spikes upward first before gradually falling as the picture becomes clearer. With 2024 YR4, observatories around the world trained their instruments on it immediately. Data came in from ground-based telescopes across multiple continents. Each new observation was fed into orbital modeling software. The solution slowly sharpened, and as it did, the probability of an Earth impact in 2032 began to fall. By February of 2025, the Earth impact probability had dropped significantly. Further observations continued to refine the orbit. Eventually, the possibility of 2024 YR4 striking Earth was effectively ruled out. the asteroid would pass through the inner solar system without hitting our planet. That was good news, but the story was not over. Even as the Earth impact scenario was being resolved, a separate question emerged. If the asteroid was not going to hit Earth, could it still hit the Moon? This might seem like a secondary concern. The Moon does not have cities. It does not have ecosystems. A lunar impact would not be a human catastrophe in the same way an Earth strike would be. But an impact from an object of this size would still be scientifically significant, and the question was real enough that it kept the asteroid on the priority list of tracking programs worldwide. The estimated probability of a Moon impact peaked at around 1.7%. Small, but notable. Scientists wanted to resolve it definitively, and the orbital uncertainty that remained after the Earth impact was ruled out was still wide enough that a clear answer required better data. Ground-based observatories had done a tremendous amount of work to get to this point, but to take the next step, to pin down the orbit precisely enough to resolve the lunar impact question, scientists needed something more powerful. That is where the James Webb Space Telescope came in. The James Webb Space Telescope, known as Webb or JWST, is the most capable space observatory ever launched. It sits at a gravitationally stable point in space about 1.5 million kilometers from Earth, in the direction away from the Sun. From there, it observes the universe without atmospheric interference and without the interruption of Earth's day-night cycle. Webb was designed primarily for deep field astronomy, studying distant galaxies, early stellar formation, and the atmospheres of planets orbiting other stars. But it is also an extraordinarily sensitive instrument for observing objects far closer to home, including asteroids. In early 2025, observation time on Webb was allocated specifically for 2024 YR4. Getting that time was not automatic. Webb is a shared resource used by scientists around the world for a vast range of research programs. Allocating it to track a near-Earth asteroid speaks to how seriously the planetary defense community was taking the situation. Webb observed the asteroid using its infrared instruments. Infrared observation is especially useful for asteroids because it measures thermal emission, heat radiating from the surface of the object. This data allows scientists to estimate the physical size of an asteroid more precisely than optical data alone can provide. Here is why that matters. When you observe an asteroid in visible light, what you are seeing is reflected sunlight. The brightness of the asteroid depends on two things: its size and how reflective its surface is. That reflectivity is called albedo. A small, highly reflective asteroid can appear just as bright as a large, dark one. So brightness alone does not tell you how big an object actually is. Infrared data breaks that ambiguity. The heat an asteroid emits is directly tied to its size and how much sunlight it absorbs. By measuring the thermal emission, scientists can determine the actual physical dimensions of the object with much greater confidence. The Webb observations gave scientists a significantly clearer picture of 2024 YR4. The refined size estimate settled toward the lower end of earlier predictions, approximately 60 meters across, with some remaining uncertainty. More importantly, the precise tracking data from Webb's observations allowed scientists to refine the orbital solution one final time. The result was clear and unambiguous. The probability of 2024 YR4 impacting the Moon in 2032 dropped to essentially zero. The asteroid would pass through the Earth-Moon system without striking either. The case was closed. NASA announced the resolution in mid-2025, and the broader planetary science community confirmed the finding. 2024 YR4 had gone from one of the most closely watched objects in the sky to a fully resolved non-event. Exactly the outcome that planetary defense programs are designed to produce. It is worth pausing on that phrase. A resolved non-event. In public conversation about asteroids, there is a tendency to treat a confirmed non-impact as an anti-climax. All that attention, all that tracking, and the answer is just nothing happened. But within the planetary defense community, a resolved non-event is not a letdown. It is a success. The system worked as intended. An object was detected early, tracked carefully, analyzed with the best available tools, and the risk was assessed accurately. That is not a disappointment. That is the whole point. The 2024 YR4 story matters for several reasons beyond the immediate result. First, it was a real-world stress test for the entire planetary defense infrastructure. The global network of sky surveys, the international coordination between space agencies, the allocation of time on the most powerful telescope ever built, all of it was mobilized in response to a genuine, if ultimately non-threatening, detected risk. The coordination worked. Scientists from different countries and institutions shared data, compared models, and reached a consensus. Second, the involvement of Webb in this tracking campaign opens up new possibilities for planetary defense science. Before Webb, precise infrared observation of small near-Earth asteroids required either a dedicated space-based infrared observatory, like the WISE mission and its successor NEO-WISE, which ended operations in 2024, or ground-based telescopes working around the limitations of Earth's atmosphere. Webb is far more sensitive than anything that came before it. Its observations of 2024 YR4 demonstrated that it can contribute meaningfully to planetary defense work, even though asteroid tracking was never listed among its primary design goals. Third, and perhaps most importantly, this event reinforced just how critical early detection is to the entire system. The reason scientists were able to get a definitive answer on 2024 YR4 7 years before its closest approach is that it was detected with enough lead time to allow a full follow-up campaign, multiple observatories, multiple data sets, Webb observations, a complete orbital solution. If that same asteroid had been detected with only a few months to spare, the situation would be very different. The same campaign that resolved the risk so cleanly might not have been possible. Early detection is not just useful. In scenarios where action might actually be needed, it is potentially the difference between having options and not having any. There is also something worth saying about how uncertainty works in science and how it sometimes gets misread from the outside. When a 3% impact probability was announced, some coverage treated it as near certain doom. Other commentary dismissed it as statistically negligible. Neither framing was quite right. A 3% probability is genuinely worth taking seriously. It is also far from a certainty. Scientists held both of those things at once, mobilizing significant resources to investigate, while communicating clearly that the most likely outcome was a safe pass. That balance is difficult to strike in public communication. It requires a level of comfort with uncertainty that does not always translate well into headlines. But the planetary defense community has learned, through years of experience with objects like Apophis and others, that transparency matters. When scientists announce an elevated impact probability, they are not trying to cause alarm. They are sharing the current state of knowledge honestly and inviting the public to understand how the process works. The resolution of 2024 YR4 is a good example of that communication working well. A concern was identified, explained, investigated, and resolved. The public could follow the story from beginning to end and come away with an accurate picture of what happened and why. As for the asteroid itself, 2024 YR4 will continue on its orbit around the Sun. It will make a relatively close pass through the Earth-Moon system in 2032 as calculated, but it will not strike anything. Scientists may choose to observe it again as that date approaches, not out of concern, but because the close approach will offer an opportunity to collect additional data and refine the orbital solution for future decades. One factor that scientists will want to keep accounting for over time is something called the Yarkovsky effect. It is a small but real force that arises from the way asteroids absorb sunlight and re-emit it as heat. Because of an asteroid's rotation and the uneven distribution of that heat emission, there is a tiny net push acting on the object continuously. Over decades and centuries, that push can meaningfully shift an asteroid's orbit. For any long-range impact calculation, looking 30, 50, or 100 years into the future, modeling the Yarkovsky effect accurately is essential. And modeling it accurately requires knowing the physical properties of the object, its size, its rotation rate, its surface composition, its shape. The Webb observations of 2024 YR4 contributed directly to that knowledge base. Even a resolved non-event adds to the catalog of data that makes future tracking more reliable. We are living in a period of genuinely rapid progress in planetary defense capability. 2 decades ago, the global detection network was far less complete. The analytical tools were less sophisticated, space-based infrared observation was limited, international coordination was less mature. Today, the combination of automated ground surveys, space observatories like Webb, and increasingly capable orbital modeling software gives the scientific community tools that earlier generations of asteroid researchers could only imagine. New survey programs are accelerating the pace of discovery. The Vera Rubin Observatory, which began science operations in 2025, is designed to push detection of smaller near-Earth objects significantly further. The goal is to find more objects earlier and to give the global community more of the lead time that makes a real difference. The story of 2024 YR4 fits into that larger context. It is one well-documented example of a system that is actively improving, being tested by real events, and producing reliable results. No one is suggesting that every future detection will be this straightforward. Some objects will be harder to track. Some will require faster responses. The goal of planetary defense is not to guarantee a perfect outcome in every conceivable scenario. It is to be prepared, to have the detection infrastructure, the analytical capability, the international coordination, and, where necessary, the technology to act, all in place before they are urgently needed. The 2024 YR4 story is one data point in that ongoing effort, and it is a good one. An asteroid was found. It was watched closely. The risk was assessed honestly with the best tools available. And when the data came in, the answer was clear. Earth is safe. The moon is safe. And the systems built to reach that conclusion performed exactly as intended. That is not a small thing. It is the result of decades of work by scientists, engineers, and institutions who understood that the question of asteroid impact is not if a dangerous object will eventually be found on a threatening trajectory, but when, and whether humanity will be ready when that moment comes. For now, with this object, the answer is yes. We were ready, we watched, and we can move forward knowing the system works.